Thank you, Marco. As Marco said, I used to be a professor of economics, and then I left to go and work on renewable energy. I still have an appointment at Harvard, so I continue to teach an undergraduate seminar on renewable energy over there. But most of my time is spent working on heat pumps with thermal storage, because I think we are going to enter an interesting time in the energy transition, and space heating is a major part of what we need to get right. So I'm going to talk about two things today. As Marco said, I'm going to talk, in the second half, I'm going to talk about space heating in Maine, but I'm going to spend a little bit of time talking about the electric grid to start. When I was a kid growing up, if you wanted to be a self-sufficient person, you had to know how to take apart an internal combustion engine and put it back together. Otherwise, you were going to break down somewhere and you weren't going to be able to get home. I don't think that's going to be true for very much longer. I think we're going to have to learn how to fix electric motors. We're all going to have to learn about how electricity works, about volts and amps and watts and impedance and all of those things that everybody learned in high school and promptly forgot. And so this is going to be an important part of what it means to be able to understand our own lives. So I'm going to talk about renewables challenge, and then that's going to involve talking a little bit about the grid and what could anybody possibly mean by the problem of abundance. And then I want to talk about electrification, building electrification, and thermal storage. Okay, so a little bit of data. So this is electricity prices in Southern California from last May. And what is shocking about this picture is that the wholesale price of electricity in Southern California every single day that week went to zero or below. Electricity at the wholesale market in California was free in the middle of the day every single day. This is not unique to California. The bottom picture shows what the difference in wholesale prices in New England between a cloudy day and a sunny day in the first quarter of 2024. This is a picture of wholesale electricity prices in the Midwest. I've got a bunch of these. You can look at these all the time if you want to. They're incredibly interesting. The interesting thing is the purple splotches, which are negative prices around wind farms. Negative prices around wind farms. Negative prices around wind farms. Many, many days you will see. This was this morning at 6 a.m. Okay, many, many days you will see negative wholesale electricity prices around renewables facilities. These are electricity prices in the community that we are building heat pumps with storage in Maine. You can see the electricity prices went negative about 15% of the hours during the heating season. More than that if you restrict yourself to looking at the heating season. So this is a real opportunity, of course. That means electricity is free. If you can figure out how to access it, that's a non-trivial regulatory problem that we're working on, making sure that regular old customers can actually get access to wholesale prices. But we'll be able to solve that problem. And this is not a temporary problem. Every single long-term model of a decarbonized energy system includes large amounts of renewables curtailment. This is the Princeton study called Net Zero America. I believe this is a 2040 study, and those pink things that happen every day are renewables curtailment. This is a study from ISO New England, also 2040. These are negative prices going on. So we're heading for a time of intermittent cheap energy when energy is abundant, right? So what does all this mean? So variable electricity prices at the wholesale level tell us something real about scarcity and abundance. And what they tell us is that just because of the economics of renewables and the economics of storage, there are going to be times that we have more electricity than we know what to do with. Electricity prices on a low carbon grid vary vastly by time and place. Right? At certain times and in certain places, electricity is going to be cheap. Now, of course, there are the dual solutions to time variability and place variability are storage and transmission. You would not see this pattern of prices in the Midwest if you could move the electricity across from the purple zones to the orange zones, but you can't. The electric grid is simply not good enough. And similarly, you would not see these negative prices if you could move the energy out of that region, and you would not see these negative prices if you could store it from the middle of the day to the end of the day. So one solution to this problem is transmission and storage. But that turns out to be a fantastically expensive solution, and we've got a cheaper one available to us. So these low and negative prices are driving returns to renewables developers down, because who wants to build a wind farm if you're going to get curtailed off 20 or 30% of the time? It's causing them to ask for ever higher subsidies for both energy and storage in order for them to keep building, and these subsidies are being paid for through increased electricity prices. So while it looks like electrification is the solution, and more renewables, that these two things work together, in tandem, going down the track. Oh, great. More renewables, more electrification, soak up that excess energy. I think this is a better picture to describe where we're heading. Okay. And I'm going to talk about why I think that is. Okay. So electrification of space heating is critical. Space heating consumes 50 to 20% of US energy and contributes 15 to 20% of carbon emissions. You all know these numbers. You've seen them before. Heat pumps are the preferred electrification solution. As we just heard from Samantha, heat pumps consume substantially less energy than what they replace, certainly than resistive electric heating, but also than fossil fuel. But we have to be careful about this, because heat pumps are problematic for the grid. And they're problematic for the following reasons. First of all, heat load itself is highly peaky, right? The amount of heat required on the coldest day of the year is 3 times as much as the heat load required on the average day of the year during the heating season. Okay, 5 times the average for the year and 3 times the average for the heating season. Okay, so heat load itself is very peaky, but heat pumps have a double whammy because, and I'm not going to go into the physics of heat pumps right now, but heat pumps, so-called coefficient of performance, the efficiency with which they turn electricity into heat, goes down as the outside air temperature goes down. Right, so on temperate days, on 40-degree days, you can generally get about 3 times as much heat out of the heat pump as the energy that you put in, or the electric energy that you put in. That's called a COP of 3. On really cold days, that COP drops to between 1.5 and 2, especially for air-to-water heat pumps. And so on really cold days, the heat load goes up, but the electric load goes up by a whole lot more. Right? And so this is a picture from a study that was actually done in Great Britain almost 7 years ago now, but showing just how peaky the heat load, the electric load is for a heat pump heated house. Okay, so what does this mean? This is a little simulation that I did from New England. Is what happens if we've got 25% penetration and 50% penetration of heat pumps on the New England grid. And as you can see, on a cold morning, we would blow away. This dotted line is the highest all-time load in ISO New England, right? And we would be exceeding that with only 25% heat pump penetration, which, by the way, we're going to be at real soon in New England. We're putting in heat pumps like crazy right now. So this is something that we really have to pay attention to. So Samantha was talking about how much less energy these systems use, these heat pumps use, than the systems they replaced. But what we're not thinking enough about is the fact that electricity per kilowatt hour is way more expensive than natural gas per kilowatt hour. Electricity per kilowatt hour in most places runs 7, 8, 9, 10 cents. In New England, it's more like 20 cents a kilowatt hour. Gas is like 4 cents a kilowatt hour heat. Okay. And so what that means is that in way more than half the states in the country, if you replace your gas heater with a heat pump, you are going to pay more for your heating bill. Okay, and this is true. This is one study. This is another study done by a colleague of mine at Harvard, Dan Schrag. This is this is color coding the savings by state. Actually, I think they do it at county level from installing a heat pump, and you can see that in every single state where it's cold, it is more expensive to heat with a heat pump than it is to heat with natural gas. Right? So we have to address this problem. Notice, it doesn't matter how much you subsidize the heat pump. If the operating costs are higher, it's going to be really hard to get people to adopt them. Right? So we're going to have to address the operating costs. How do we address that? Well, we're addressing that in Millinocket, Maine in the following way. If you could actually capture these times of really cheap electricity, all of a sudden heat pumps start looking super cost effective. right? Because the cost of electricity drops like crazy. Okay. And so that's what we're trying to do in Millinocket. The problem is heat load is not very flexible all by itself, right? Ask yourself this question: in a cold place, how long can you turn off your heat? How many hours can you turn off your heat for before you start being uncomfortable? And if you can shift even 2 hours, you've got a really tight house. Okay. So what we need is a way of shifting that electric load off of the peak times and into the trough times. Most importantly, shifting that load into the times when electricity can be and is really, really cheap. So a standard heating system looks like this. You have a heat pump, you have a load, and when the house calls for heat, the heat pump comes on. It's an incredibly simple control system, nothing complicated about it. What happens when you add storage? Well, when you add storage, the control problem becomes harder, right? Because you have to be able to do three things. You have to be able to heat the house from the heat pump. You have to be able to heat the house from the store. And you have to be able to heat the store from the heat pump. This is something that we call a flow control module. Those are the three functions that you have to be able to do if you want to be able to use thermal storage, that is tanks of hot water, to allow the heat pump to run when electricity is cheap, but keep the house warm all the time. You need a SCADA system that monitors the heat pump, the storage, and the house, gets forecasts about weather and prices, and makes a decision about what the flow control manifold needs to be doing every hour of every day. Looking forward, saying, oh, it's going to be windy in Minnesota. I think I'm going to try and not buy energy now, but get through as best I can so that I can buy energy like crazy when the price of energy drops. This is a picture of the systems that we're building. We have 3 installed starting in October. We have 2 more being installed right now. You can see these are the tanks of water where the heat is stored. That's a buffer tank for buffering what comes out of the heat pump. This is the flow control manifold and the SCADA system right here. That's me and my good friend Paul Moscone, who is our installer up there in Maine. So very quickly, this is a picture of what we're doing. I don't expect you to follow this except to see that we're collecting all kinds of data at very high levels of resolution. This is the output of the heat pump. And when the heat pump is running, this is the output of the distribution system. So you can see we're putting roughly 150-degree water into the house, coming back at about 130 degrees. So about a 20-degree delta T in the heating system, just about what you would like. These are the heat calls. This is a 4-zone house. You can see we're getting nice, kind of steady periodic heat calls, just what you would like to see. And this is a very cold day. So these are sub 5 degree, almost down to 0-degree days in Millinocket, Maine. This is the state of the buffer tank. This is the state of the storage. Okay, so what is possible in Millinocket? Okay, well, where we're heading towards is building a model where we predict when the wind will be curtailed in Millinocket and make sure that the storage tanks are empty. So then we can run the heat pumps as hard as possible when energy is free, essentially free, and store that energy until it's needed. On a temperate day, we can keep the house warm for about a day and a half on a full set of tanks. On a really cold day, a day and a half is probably a little bit more, probably maybe a day. On a really cold day, we can store 5 hours of heat, and you can see us doing it right here. We turned off the heat pump at 7 a.m., and we did not turn on the heat pump again until noon, and the house was warm the whole time. Okay, so we've got 5 hours of storage even on very cold days. Our models show that we can reduce the cost of heating from about $3,000 a year using oil to under $800 a year buying electricity that would otherwise be thrown away from curtailment at the wind farms. Okay, look at that. I'm going to make it on time. So we believe that we're on the verge of making a major infrastructure mistake by installing heat pumps without storage. We are ignoring a looming grid problem that can be easily solved. We're installing lots of air-to-air heat pumps. There is no way to add storage to an air-to-air heat pump. Samantha was completely right. You know, if you use your heat pump to make water, you can use it in a hydronic heating system. You can also use it in a forced hard air system by simply putting a heat exchanger in the plenum. Okay, so you can if you start with an air-to-water heat pump, you can use any existing distribution system. And just for a quick point of comparison, when I said we could store 5 hours of heat on a really cold day with 320-gallon tanks of water, that would cost you about $50,000 in chemical batteries. You'd need 4 power walls to do that. So it's and all in those tanks cost about $1,000 a piece. Installed, we figured the storage system costs about $4,000 in our basements in Maine. So it's just a substantially cheaper solution than trying to store with chemical batteries. The technology, as I say, works for any residential or commercial heating system, forced hot air or forced hot water, and as every model shows, storage is the key to a reliable low carbon energy system, and thermal storage is the most effective storage technology available. So that is, I'm look at that. I'm 1 minute early. I hope there'll be some time for questions.
Well, thanks, George. This is great. We have a few questions. I think we have time probably just for one. I'm just gonna probably ask what Colleen asked, which is Alaska is another place where they have rural places with oil, and she's asking if you have data on that. Maybe you guys can connect offline. That sounds like another great area for your application.
We looked at Alaska actually a few years ago with the company that I helped to start. Alaska is just a tremendous opportunity. There is lots of available renewable energy, especially wind, but also some solar. Not so much solar in the winter, unfortunately, but very poor connections. So nothing to do with it, right? And so finding a way to use wind energy to keep buildings warm in Alaska is a great solution, and thermal storage is a great way to do it. So I don't have much data on it. We talked to a bunch of people, but you probably know those people already. But yeah, there are real opportunities. Islands, by the way, are another great opportunity for this. Once again, they tend to have weak grid connections. They tend to have very good wind resources and no way to move the power off. Shetland Island, for instance, is a place that's struggling. They have capacity factors on their wind farms of 60%, and they can't build any more wind because they have no cable. They got nothing to do with that essentially free energy. They're looking at storage heat like crazy to try and figure out how to use that and save it for times when the wind isn't blowing.
Awesome. Thanks, George, on behalf of everybody who's been attending, and thanks everybody. I'll see you at the next talk. Bye-bye.